So, good morning, afternoon, evening, night, everyone. Welcome to Technology Deep Dives on the DNS. The Technology Deep Dives are a series of talks where we discuss a topic in depth and provide a focused exploration of the technology. They are designed to be interactive, but this is likely to be a little easier to do virtually, but we're going to give it a try. This session is being hosted both on Meet Echo and is also being streamed on YouTube. It is also being recorded and will be posted later. But we're only going to be handling comments and questions in Meet Echo. We're not likely to see any questions that you post in YouTube. So previous deep dives were on modern router architectures and how network interface cards work today. At the end of those sessions, we sent out surveys, and DNS was the most requested topic for a future session. So while preparing a session on DNS, we realized that there's more than enough content to fill many, many, many hours. The session is only 90 minutes, and so it's mainly going to have some introductory stuff and some deep dive, but we're likely to have at least one more session on DNS, including things like myths and misconceptions. That will likely happen at IETF 109 or IETF 110. And with that out of the way, and because we have more content than we have time for, I'm going to hand it over to Wes. Take it away.
All right, thanks, Warren. Hopefully everybody can see my slides. I think Barry indicated that he could. So the three of us are going to go over stuff. We'll start sort of high level, but we'll dive pretty deep into various parts. We will do in the future security related stuff. This is a IETF event, part of IETF 108. Welcome everybody to IETF 108. This is besides the hackathon, this is one of the earlier things that are happening. I hope you have a great week next week. Please do note that the note well for the IETF does cover this event as well. I'm not a lawyer, so I won't attempt to summarize it for you, but you ought to go read it on the IETF website if you have not done that before. Today, we're going to be going over sort of three major topics. I'm going to talk about DNS basics and beyond the basics. Jeff is going to talk about the resilience of the system, and Joelle is going to talk about the DNS software and the APIs. There's a lot that we are leaving out that we will cover at possibly a future session, as Warren indicated. So this is how the average internet user sees it. We've at the IETF have designed things well enough that we hide a lot of the complexity in many protocols, the DNS included. They want to go to a website, they type a website in, and they think they get everything back from some machine. They don't understand quite how it works, and the technical person typically knows a little bit more, right? They know that they have to look up an address in the DNS first, translating the name into an IP address, and that's done by DNS, and then they do HTTP or HTTPS to a server to actually get the answer. The DNS is a lot more complex than that. We're going to go over bits and pieces of this whole diagram, but there's lots of devices and boxes involved and lots of servers involved just to even complete one web page. And actually, as an example of that, example.com, as many people know, is a domain owned specifically to deal with documentation and things like that. It's one of the things that we put into IETF documentation. And this is what a web page generates. If you open your web browser and you go to www.example.com, these are all the DNS requests that get fired off. Each line is an individual DNS request. None of them are HTTP. The resolver in this case is actually sort of the node in the middle, and the edge node is a note that there's actually only one line from the edge node, which was my laptop, to the other one. The IETF.org website actually has more resources on it, and the end result is it causes a whole lot more DNS requests. You get to some of the bigger websites that have tons of things, including ads and JavaScript and all sorts of external resources, and it actually causes a huge number of DNS requests, and most people have no idea that this is happening behind the scenes. Caching, which Jeff is going to talk a lot about later, really helps this, where DNS actually, the resolvers actually memorize answers for a while based on the data. We'll talk about that and the time to live values later. But there's still a huge number of requests coming from you to your ISP most of the time, or you to your resolver most of the time. And even with caching, you can see that there's a lot of other bubbles that were new, that were not cached information from dynamic content and things like that pop up new data. So we're going to break things down. At first, I'm going to go into the underlying distributed model of the DNS. The DNS is a very distributed protocol. And it was really created as a replacement for just static host files way back in the beginning of the internet. People were shipping around these static host files of addresses and names associated with them, and then they'd have to update them on a regular basis. And that got unwieldy and clearly doesn't scale to the millions of names and addresses that we have out in the world today. So the vision was we created this tree of information. Tree is sort of a misnomer because it really looks more like a root structure than a tree, but it's still called the DNS tree. With the root at the top, a lot of people don't even know that the root exists. They think that net, com, org, and all the top level domains are really the top, but there actually is a system above that, which we'll talk a little bit more about. And then there's second level domains, things like example.com is one, and ietf.org and icann.org as some other examples. This diagram is going to repeat a lot. I am not showing all of the other components of the net, com, org, and root zones because the .NET zone, for example, has 13 name servers associated with it. Would be other bubbles around, and so does com, and org has 6, and the root has 13 as well. But to simplify it, we're going to limit these diagrams mostly to just be talking about the lower level leaves in terms of complexity and their content. So what is a resolver? Well, when you type something into your web browser or you open any sort of internet connection, because the web is not the only thing that uses the DNS or the internet for that matter, it opens a request to your ISP, typically your DNS resolver and the ISP. And the job of those boxes, including the cloud-based ones that are talked about a lot in the IETF lately and in other places, the job of them is to go actually traverse this tree to find the answer that you need and then return it back to you. There's a good number of types of resolvers, and there's a good number of boxes that also may exist. Your wireless box often acts as a resolver. The hotel paywall type, thing where you have to prove that you're in the room, or a coffee shop or something like that, acts as a resolver as well and treats them differently. Joao is going to talk a lot more about them later, but there's stub, recursive forwarder, and validating. He'll talk more about what each of those are near the end of the talk. Priming queries, bootstrap resolvers. When a resolver starts up, it really doesn't have any clue about what the world looks like. So the only thing it has is a hard-coded list of addresses of where do I get started. And the first thing it does is it starts up and asks the root, hey, is my list up to date? Where do I get started? Where are the 13 points on or 6, really 20. Excuse me, 26, 13 for IPv4 and 13 for IPv6. Where do those exist in the world? How can I contact them so I can find the rest of the tree? So this is called a priming query. You'll see that in a lot of documentation and in a lot of discussion. The DNS is a distributed protocol, and it does that by delegations. And so each zone is allowed to delegate any sub-portion of its name structure within it to a different zone, where a zone is sort of a collection of names and information associated with one particular point in the tree, and delegations occur lower. So for example, the .NET zone delegates IANA servers, the name label IANA servers, to IANAservers.net, and it does this using name server records, which we'll talk a lot more about. By giving clients references to here's where you need to go. So a quick little bit of DNS terminology, looking at the same sort of diagram. The apex of a zone is another commonly misheard and misunderstood name. It is the top level name associated as sort of the entry point into a particular zone. It's the name of which a delegation actually arrives at. Oops, wrong key. Other nodes, of course, can exist. The leaves, if it's the end of a tree, right? It's the bottom node in a tree. You'll find that it is called a terminal node or a leaf sometimes, but they're terminal nodes, meaning they terminate the tree. Whereas you can actually have nodes in the middle. You don't have to have each name be subdelegated. And so empty non-terminals are things like the A in b.a.example.com, where there's actually no data there, but there is stuff underneath it, and it's actually within the same zone. So when you read the documentation, you'll see things like terminal and empty non-terminal. You can come back to this slide if you ever get stuck. A couple of important things. Duplicate records are needed in both the parent and the child zones. So for .NET to be able to tell clients that come to it, hey, where is IANAservers.net, it has to have a list of where to send people. So there are 3 name servers for IANAservers.net. There's A, B, and C .IANAservers.net, and those need to be in the .NET zone to say this is where I'm going to send people, and it needs to be in the authoritative list for IANA servers. Will actually also respond with its name servers list, and these need to be in sync. So what happens if they're not in sync? What happens if .NET actually has A and B and the IANA server zone has B and C, and you can see that these particular zone records actually don't match? Does this actually work? Well, yes, but it definitely has problems and causes timeouts, as a resolver might go to A and A will either answer or it won't, but it's still the wrong place. They'll eventually go to IANAservers.net, at least sometimes. There's a whole paper studying whether that's actually true or not, and ask them for the authoritative list and hopefully update their records. If A won't answer, if A will not answer and it doesn't actually have the information for the client, this is called a lame delegation, another term that confuses people because it's sort of obtuse in terms of what it actually means. But essentially, a lame delegation means that there's a disconnect between the parent and the parent's still holding on to a name server record that the child no longer uses. So the important takeaway of this slide is if you are running, if you own some domains, make sure your parent and your child are in synchronization. So if you're running your own name servers, if you update your infrastructure, you need to tell your parent. So let's talk a little bit about how this actually happens, how the parent actually refers stuff. So let's query .com's servers about example.com. And so this dig is a popular tool that comes with ISC's bind. There's a number of others that are similar, including kdig for not, for example. They operate in a similar way where you can direct a request at a particular server, like I am doing here with GTLD servers.net is a server for .com. So if we send that server a request for www.example.com and we ask it for an A record, which is an IPv4 address, we'll get into that later, it will give back an authority section full of information. So it's going to give back 2 answers. It's going to say, hey, you need to go talk to A.IANAservers.net and B.IANAservers.net to get to example.com. So only those servers know where www.example.com is, and .com, of course, doesn't actually know the depth of the tree. It only knows where example is. But it does know where to send you. It wants to send you to IANAservers.net. But where is IANAservers.net? So you can see a resolver starts getting this whole chain reaction of, well, okay, now I have to go find this other part in the tree. And quick interjection. So you'll see these numbers a lot in all of these slides where there's this random number in the middle. That TTL value we'll get back to later, and Jeff will talk about caching later. 17280 is a 2-day TTL, which is really common for the higher level nodes and how long to keep information. But there's a big chicken and an egg problem, right? How do I get to some place in the net if it keeps referring to other places in the tree? So pictorially, .com is basically telling you when you want to go to IANAservers.net, you're going to jump over to A and B.IANAservers.net if you want to get to example.com. So it actually redirects you to a completely different part of the tree. This happens all the time. So there's another interesting one. If we ask .NET's server for where is IANAservers.net, and we say where's the name servers for IANAservers.net, it is going to answer, well, there are 4, A, C, and B, and ns.icann.org. So a completely different part of the tree again. So how do I talk to a.ionoservers.net if it's inside ionoservers.net itself? You're actually telling me to go find something inside the zone that I'm trying to get to. How do I do that? So it gives back an additional section that contains glue records. So you can see that in addition to giving you just the names of the name server, it's actually going to hand you addresses as well. These addresses need to be in sync with the parent and the child as well. If you change addresses of your name servers, you'd better tell your parent if they're within the zone in question. These are called glue records, another name that you will see frequently in the DNS literature. So the glue records are required when you have delegations when you have name servers within the zone that you're actually delegating to. The parent has to have the list of addresses as well. And of course, they should match. So pictorially about glue, .NET's name servers, as I said, know where the authoritative source for ionoservers.net is. There are 3, A, B, and C, that are within the zone itself. This is called in bailiwick, another term that you will see in DNS literature a lot. The red lines are in bailiwick, A, B, and C, ionoservers. The other arrow to the right is pointing to an out of bailiwick name server. In other words, it's handled by a completely different part of the tree. So that's sort of the overview of how tree navigation works at a very high level and how resolvers actually have to, find different parts of the tree. We're going to dive into the DNS packet and how it's sort of evolved. The stuff on the left is actually the total packet count, or the total packet. The box on the right is what each each portion of the data that's transferred around is shown as. We'll dive more into that. So the DNS itself is a very, very simple protocol. It ships around these things called resource records, which was the diagram on the right. And a resource record is composed of a triplet. It's composed of a query name, which is the actual name that most people think of, as a query type. For example, a quad A record, or 4 A's, is a IPv6 address. And it's composed of a query class, which is IN for internet. And that makes up the 99% of what exists on the internet. The rest of the classes aren't really used, with the exception of a chaos class, which is a special case. And we won't go into that today. Resource record sets, they all match. Each of those 3 is a triple match an atomic unit of data. You can't ask for just a sub-comportion of it. If you want, a name for www.example.com and you want the IPv6 address for it in the internet, you get back all the answers. You can't ask for just one or just a couple, or even hand back just parts of them. They're atomic units and are considered complete. This becomes important for security later, and it becomes important for caching as well. Note that they are not ordered. The answers that you get back may be completely different than when you ask from one time to when you ask for the next. Some people think that they are ordered. They are not, and clients don't necessarily have to keep them ordered. So even if you return them in the same order, they may not be treated that way. Response records also contain a time to live. That'll come into play later, as well as the data itself, what the address actually is, or possibly multiple addresses actually are. The DNS packet components consist of sort of 2 main sections. There's a header with a transaction ID, which is unique per transaction, or it should be. There are flags. We'll talk about a couple of them, but not all of them. And then there's the number of resources records in each section. And then there are 4 sections following that. So there should be, of course, a number indicating how many pairs are in each of the following sections, like the question, answer, authoritative, and additional. We'll come back to that. One real quick point, you note that the number of resources in each section includes the question. So the number of questions in the original request has to be there. Well, there can really be only one, except that that's not actually true. It turns out if you look at the original RFC, it actually says that you can have a QD count, or a question count, of greater than 1, but that is not used today, though the packet format actually allows for it. It's not actually usable, and really there's a number of problems that people realized early on, like what happens if you're querying for multiple things? Well, do you wait for all of the answers to come back before you return it to the client? What happens if one has an answer and one has an error? What happens if there are 2 different errors and they're not even the same error code? And they realize the complexity of that. It would be better to fire 2 questions off in different packets and different requests than to try and bundle them into a single one. Quick point note: there's probably few people that get both of these references on the right. If you don't understand the bottom one, go ask somebody over 40. If you don't understand the top one, go ask somebody under 20. Anyway, DNS packet sections. So the question, where the single question goes, that's where the question goes in the packet. It's repeated in the response, so the client that gets the response back should have the question that it can look up and say, oh yeah, that's what I asked. The answer to the question, of course, would go into the answer section. There can be multiple answers, of course. There's the authoritative section. This is a really critical section that says, what is the owner? Where are the name servers that own this portion of the tree? Who should I go talk to make sure that this is the authoritative source? Or maybe the authoritative source is who you're talking to, but it references who actually owns that portion of the tree. And then there's an additional section. There's lots of helpful stuff that goes into the additional section. We'll talk about some of them today. And it's anything else you should want to know, but you really can't trust. So if, for example, glue needs to go in there, but you should really go ask the authoritative source for what they believe their answers are. If you remember the whole notion of cache poisoning, it used to be that servers would trust anything you put in there. So you could completely overwrite somebody else's addresses on the internet. If you asked a authoritative server for a particular question and they give you a bunch of other data, you just cache it for a while. That's no longer true. Software stopped doing that when we ran into huge issues with cache poisoning. So what happens in the DNS when things actually go wrong? So how do we handle the errors in the DNS? What happens when a resolver can't do something or an authoritative server can't do something? Well, the good news is that there is a response code in the field. And one of the misunderstandings about the response code is what we're going to go into next and how it is actually handled. And it gets a little bit complex because we've really kind of tinkered with it over the years. You'll notice that the R code on the right-hand side is the last 4 bits of that packet header for DNS, right there. The problem is there's only 4 bits. So we have come up with a lot more reasons for having errors than I think was originally envisioned. And there are certainly way more than 16 problems and way more response codes that could indicate something. So people got creative about the whole R code problem and about other problems. How do we extend the DNS in general when there's no more packet space? Well, this is true for a lot of protocols. There's not a lot of extension room. Well, what if, now hear me out, what if we stuck those extra bits somewhere else and then we smashed them all together later, right? We just extended the packet. And so thus a very creative hack called the opt resource record was created. And it was put in a specification called EDNS0, which is RFC 2671. It is an extended pseudo resource record that adds data to the additional section. Clients have to say that they support it. They have to send one first before servers will send one back. And it's required by some protocol modifications like DNSSEC. DNSSEC simply won't work without EDNS0 support. Most software these days does support it. And it reuses the resource record byte format. So it actually is a resource record in itself, but it's sort of a pseudo one because software strips it out. And it changes many of the fields to mean completely different things. So for example, the features of it include a much larger error code that comes out to 12 bits now. It supports additional protocol flags that are needed for things like DNSSEC. And it adds a sort of an MTU path-like discovery for max message sizes that software can actually handle based on what it thinks it can get through its local network, for example, at the application level, not at the IP level. It adds support for additional DNS extensions, and there's a few of those that exist today. I did not enumerate the whole list, but client subnet is a common one that a lot of people know about, which is used by CDNs, as well as extended errors, which we're going to talk about very shortly. So the opt resource record field reusage, as I said, they take the resource record field and then they just reuse various components of it, so it can still be parsed easily. There's a name, but it must be empty, so the name is actually blank. It's a null name, basically. The type value is 41. That is the opt type code assigned by IANA. There's a class. So instead of putting in class, which as I said was internet before for most resource records, we transform it into the UDP payload size instead. So you get 16 bits to say, this is the maximum payload size that I can accept. Please don't send me anything bigger than that. The TTL, which is normally 32 bits of how long you can cache data, turns into 3 different fields. There's an extended response code, which is the other 8 bits that I talked about. and a version field, which should always be 0. That's the eDNS 0 version field with specification for the opt extension, and 16 more flag bits, which are some of which are now used. And then everything else is just tag attribute value pairs and variable lengths, and multiple things can be added, so you can have multiple extensions exist within one opt field. So what happens? One of the bits in the original thing is the response is sorry. One of the original bits in the original header is called the truncation bit, and it basically says you tried. I can't send you as much information as you asked for. You're going to have to, come back with a different question, a smaller question, or come back over TCP so that, with a bigger payload size. So this happens, for example, when the opt resource records max message size was going to be overflowed. So the first thing that happens is the truncation bit is set, and then different implementations do different things. Some try and remove the unimportant items and shift the rest of the information back, so hopefully you get at least something. Some servers actually drop everything and just tell you to come back over TCP. And note that response rate limiting is a DDoS defense that is commonly deployed these days that triggers the TC bit if you start asking sort of the same question over and over and over from a single address, because that used to be used heavily over UDP to do packet reflection, and that's actually stopped a lot of the packet reflection attacks. Anyway, clients have to come back over TCP to get the full answers. It turns out that Jeff has measured that some of them don't. They got enough information that they saw in the answer, and they didn't need to come back to get the rest. All right, so what happens if you get more, if you need more errors? Just the response codes themselves aren't necessarily always enough. What happens if you have, like multiple errors or two exist, or you want to augment some debugging text? Well, what if we actually kind of stuck that data somewhere else too? So coming up soon is an extended errors. There's another opt resource record that goes inside the opt resource record, which means that we have the header with the first 4 bits, the opt record with 4-bit with an additional 8 bits, and now we're putting other errors inside of that. So it's really errors all the way down. You sandwich stuff into protocols where you can when you need to extend them. So let's dive into some of the other resource record types. The opt was a special case, but let's look at the more normal ones for a bit. So resource record types, the obvious ones, most people know most of these. There is a record, which is an IPv4 address. There's a quad A record, which is an IPv6 address. There is a SOA, which gives sort of some zone information, and it's at the tip of the apex, and it talks about negative caching and a bunch of other stuff and the serial number of the current zone and things like that. I won't dive into the details. There's a text record, which is really just a free-form text blob. We'll talk a lot more about that one in a second. But first, let's talk about happy eyeballs, which is 8305. So happy eyeballs, people realize as we're trying to deploy IPv4 and IPv6, how do we decide which, address family to use? How do we, deal with the fact that users really don't want to wait a long time? So you can't, query for v4 and then wait, and that didn't work, so then go to v6 or vice versa. So the solution is, we're going to follow this step. We're going to go send a quad A query out to say, hey, where is www.example.com? And the resolver will start chugging away at that. At the same time, the client is going to send another request immediately thereafter. It's going to start with v6, and then it's going to send another one saying, oh, and I want the A record too, the IPv4 record too. Just give them back to me when you got them. And that resolver is going to work on both of those at once. And then then your client should wait for the answers from either query. If the response that came back was a IPv6 record and quad A record, you get to open the connection. Yay, we're done. If the response is an IPv4 record, an A record, then you're supposed to wait a bit, like 50 milliseconds is what the document recommends for a quad A record. And if you don't get one, then you just give up and continue with IPv4, with sadness. But either way, you profit because you have a dual stack deployment that actually is able to do both, and you do them, in flight at the same time with minimal delay. The other common thing that is frequently misunderstood is how to properly use CNAMEs and DNAMEs. So CNAMEs are really aliases for other portions of the tree. They can be in the same zone or they can be in a different zone. And DNAMEs are aliases for the zones themselves, sort of the entire zone. So here's an example of a CNAME record in red, the top line, which is js.example.org, with a TTL of 3,600 seconds is a CNAME to javas.example.com. So it's pointing from one zone into a completely different zone, saying if you want to get to js.example.org, you should really use this other name. A lot of resolvers will also return the address for the other one too if it's within zone or they know it. A DNAME, on the other hand, is aliasing an entire zone. So it's aliasing one apex to another. So example.org may say, well, I actually, just if you come to me, I really want you to go to example.com, where aliases for each other. So anything inside of me should go over there. Important rules: CNAMEs must exist alone at a name. It shouldn't have other information and associated at the same name, except for DNS-sec records, which sort of change that a little bit. And then CNAMes point to all other types. You can't just have a CNAME for just an A or a quad A record. If you have a CNAME, it points everything to the other name. That includes name servers, MX records, serve records, anything else that might exist, text records. MX records are mail exchange records, and they really kind of answer the question, where should email for a domain name be sent? It's a prioritized contact list of where mail should be sent. And so they can exist at leaf nodes. So for example, www.example.org has this long IPv6 address. It doesn't have this one in red, but it's an example, a pseudo example. We're saying, instead of sending the mail to me, because I actually am not a mail server, I want you to send it to smtp.example.org instead. So this other box is going to handle mail for me. You can also, it's very, very common to have, if you have Wes at example.org, where does that mail go? And, the mail server doesn't exist typically at the top level of the apex of the zone. No, it's handled by something else. But more importantly, it can be handled by a completely different zone. It's very common. This is how outsourcing of mail happens, when organizations outsource their mail to some mail provider, of which there are, many. And in fact, that's much more common than hosting your own mail server these days. And this is done with MX records. Wildcards, nobody seems to understand and get right. I'll be honest, I don't use them much myself because they can be kind of complex. But if you go read RFC 4592, you'll find it's actually very clean and very well written, much better than the original text. But it generates responses for missing data. The leftmost label must be an asterisk, and only an asterisk. You can't have foo star or star foo. It has to be star dot, period, end of sentence. It matches any label that doesn't exist underneath it, including sublabels underneath it. It causes a name server to synthesize an answer. It should be an answer, not and answer. It synthesizes an answer on the fly, and it'll answer for anything the client asks for. There's really good examples in 4592. I've included some down below that are sort of the minimal ones, but 4592 has much, much better ones, including what happens when you have a label against an empty num-terminal using a term from before. So in these two examples, there's star.example.com, which says for an MX record, if anybody asks for an MX record in star.example.com, I want you to return mail.example.com unless that record already had an MX record associated with it. It doesn't. Wildcards don't override existing things. So there's some example responses down below where the MX records match for either one, because neither one of those hosts had an MX record by default. But asking for an A record never matches. Underbar labels are another, was there a question? Nope. Underbar labels are another thing that has been really popping up a lot lately. In fact, if you look at the RFC numbers, it's 85.5.2 and 5.3. They're much more recent RFCs. A long time, so the right thing to do is when you're adding new information to the DNS, a new type of information, is really to create a new RR type. You can ask IANA for one. You need a specification. I think it has to go through expert review. It doesn't have to be an RFC, if I recall. And but they're slower to deploy. It's slower for resolvers actually understand them immediately because it's just a number. It's actually not necessarily a name. And almost everything can understand them immediately, but it's harder to put into a zone file because there's not a, when you're writing DNS records, there's not a name you can associate with it. So you have to put in something strange like type 1236 or something like that. But So people started putting in text records instead, and it became a little overwhelming because they were putting text records in at the apex of zones. We had some for SPF and originally DKIM and domain key and DNS ownership verification, which is used by Google and Facebook and DocuSign and a bunch of things. Well, these all end up at text records at the top of the zone, at the apex of the zone. And you can imagine when things go off in query for these, that packet's getting bigger and bigger and bigger the more people try and stuff in there. So the right solution we decided was to use to reserve underbar as a prefix to special case names, so that instead of using SPF at the apex of a zone, it should be underbar spf.example.com. It's considered a special case, and resolvers and authoritative servers are beginning to deal with them a little bit specially as well. But the top example on the bottom 4 there is sort of the right new way for SPF. You're not supposed to put it at the apex. You should put it at underbar spf.example.com. And there's a whole IANA registry that contains all of the underbar labels that have been defined today. Underbar domain key being another one for DKIM, underbar 25.underbar TCP. You'll see those types of things, as well as underbar IMAP-s.underbar TCP for referring to specific things for a particular type of service. Service host discovery for email example is an example of the last one, where you type in your email address into a smart mail reader, and it can actually go find all of your settings for you by looking up underbar IMAP-s.underbar TCP to figure out where your IMAP server is, so the client actually doesn't have to know it. In summary, DNS is a globally distributed identifier database. The important takeaways here: note that it is distributed. It is owned by the entire world, and there's this big network of who owns different sections of the tree, and delegation happens. The amazing thing to me is that how in the world did this scale so well that we are handling this much infrastructure all over the world, and it works almost continuously. Yes, there's been some outages, but it's amazingly resilient. I have no idea how it scales so well. I have an idea. Let's go ask Jeff. So Jeff is going to dive into that next, right, Jeff?
That's the theory. Let's share a screen, and we will now talk about how it scales or not. If someone can give me a screen.
You should have it. There's a screen share button in the upper left.
Thank you. So, good morning, all. It's not even 5 o'clock in the morning yet. Oh my God, and I'm awake. Oh, the things I do for the IETF. Behind me is all black. It's not a coincidence. So this morning, I'm going to talk a little bit about how the DNS has actually managed to scale and what's going on behind the scenes. How do we engineer resilience into the DNS? And as usual, I make the tools that we have to actually engineer resilience is actually really simple. It's just replication. If A doesn't work, choose B. Now, some ways you can go, well, let's ask A and B both together. It's just a race. Who cares? The first one wins. B's hanging around in case A doesn't answer. And the other way is a little bit slower, but certainly tames the system down in terms of noise. Ask A, wait. If you get no answer after a while, ask B. In the one case, the first, ask everyone, it's really snappy and fast, but it overloads the system. In the second case, you actually put the onus on the end user, the one who's serializing the requests. The system is under less strain. You end up using all of these resources, if you have to, as backups for the originals. But the order in which you do it and the amount of strain and stress you put on the system and the time you need to actually execute that differ according to each of these approaches. So, of course, if you're considering this, you really have to think about what does a unitary DNS look like with absolutely no replication at all. And you get back to Wes's slide that here's this end resolver, this stub resolver at the end. It's configured with one recursive resolver out there somewhere that does all the heavy lifting. And that recursive resolver, at least at the start, doesn't know anything other than a root zone priming query. So it asks authoritative servers, where should I ask to find the answer? Eventually it finds the right authoritative server, there's only one of them too, gets back the answer and sends it back to the user. So this is a unitary DNS. The problem with a unitary DNS, where every stub resolver has only one, each stub resolver uses only one recursive, each domain is only served by one authoritative server with one address, IPv6 or IPv4, pick one, and each recursive resolver only sends a single query. The problem with that, of course, is you can touch any part of that and it all falls over. So you have these massive numbers of multiple single points of failure. If your recursive resolver stops answering, it's too busy, it's decided that it's a Sunday, whatever the reason, you're toast. Equally, that one authoritative server, if it fails, everything fails in terms of all the zones that it serves. And even down in transport, because it's UDP and every datagram is indeed an adventure, then if you don't get the answer, what do? And so each of these single points of failure make the DNS incredibly vulnerable to not even hostile attack. It's almost casual vandalism would take out huge amounts of the infrastructure. So this kind of model doesn't work. I mean, it just simply cannot work in any real sense. And so the answer is just simply pump up the number. And so your stub resolver, there's only one U, might be configured with a number of recursive resolvers. Now, each authoritative server might actually have a number of replicated authoritative servers. And obviously the spaghetti on the right is what happens when things go sort of badly awry. Because the theory is you can ask any of these recursives or all of them at once if you're feeling adventurous. And each of those recursive resolvers, when it's trying to find an answer from an authoritative name server, could ask one or two or all of them. And so you can send up with a massive cascading set of messages. And so the issue is, where can you put it and why? Most systems use resolve.conf or an anagram thereof. This is an original Unix-based construct, actually in the resolver library, but most systems have some kind of configuration option for your stub resolver. If you actually look at the man page for resolve.conf, which is not a bad example point, what you actually find is stub resolvers will be typically configured in resolve.conf with the addresses of up to 3 recursive resolvers. You can add more, but not necessarily a good idea. Now, in a dual stack world, if you actually use the name of those recursive resolvers, they actually have IPv4 and IPv6 addresses, and the libraries will discover that. Now, resolve.conf actually claims that those queries in using those protocols are made in parallel. Well, I'm not exactly sure that's the case. Often they're just simply made in order. But if they have v4 and v6, you'll send out both queries at the same time, well, paced by 10 milliseconds at once, which I don't think happens. The order in resolve.conf is usually important. And so if you have resolver A, resolver B, resolver C, normally you will find resolver A is hammered. Resolver B is only used if you don't get an answer from A. Resolver C is only used if the other two are dead on arrival or whatever. So that's usually the case, that order is important, although I have noticed some pieces of application software, including the Chrome browser, at some points in time started doing round robining. There's nothing wrong with round robining. It's just, what do people assume when they put stuff in resolve.conf is, are the others backups for the first, or is everything important? And the other thing is, when do you use those next ones? It's either a UDP timeout, which is most typical. You're asking a question, you get no answer, I'll go and ask the next one. But sometimes you actually get an error code, and in particular serve fail, that says, you know, I didn't answer because I didn't want to, I failed. I didn't fail bad enough that there's no answer, but I failed enough to tell you I haven't got an answer for you. Go try somewhere else. So either timeout or serve fail sends you on to other resolvers in resolve.conf. What about authoritative servers? It's certainly fashionable to use more than one authoritative server. And the root zone is a typical example. It had 13 for the anachronistic reason these days that you could stuff 13 names and 13 IPv4 addresses and fit the entire priming query answer of these 13 names and 13 v4 addresses into one packet no larger than 512 octets. but that was a different age and a different world. As soon as we added v6 to the root zone, that doesn't work anymore. So 13 is a very, very big number these days. Most folk use between 2 and 4. If you actually look and sort of comb the world's authoritative servers one way or another, it's rare to find 400 or 500 authoritative servers, and indeed insane, because you can't put them and list them in a response packet. And equally, it's kind of brave, or should I say foolhardy, to simply have only one most of the time, except for Anycast, and we'll get to that later. So the rule of thumb, which in this case is not a bad rule of thumb, 5 is probably, too many, and larger than 5 is probably, way too many, and 1 is certainly too few. Now, when you have all these authoritative servers, do you always hammer the first, or do you round robin? Well, it's up to the recursive resolver. It's up to the querier, not the server. And it may round robin, it may not. It depends on what's going on here. The list itself that the authoritative server gives back when you ask for an DNS record and it sends back a list, you might get the same list all the time. The server itself might rotate that list of servers because it wants to splay the load across all of them. So when you've got authoritative servers, 1 is too few, 13 is probably excessive, somewhere between is probably good enough most of the time. What about resilience in transport itself? Well, we use UDP for the DNS, and resilience and UDP are not things you often say in the same sentence. In fact, you never do, because it isn't. All bets are off. Now, the issue is, of course, that when UDP dies, it dies silent. Oh, I'm dead. No, you don't. Nothing happens. Crickets. And so what the UDP sender actually uses is a timeout. And depending on what it thinks it should have got an answer back in that time period, it goes, well, that's dead, ain't going to happen. Now, what timeout is being used? A lot of these timers and a lot of this code is actually based around the behavior of dial-up modems and 10 kilobit lines, 9.6 kilobit lines. And to be perfectly frank, we never changed anything. And so what you find are timers that these days seem like eons, Paleolithic periods where entire continents will move. So, stub resolvers use timeout values between 1 and 5 seconds. Oh my God. Recursive resolvers are more with it, and they typically are seen to use timeout values of between 300 milliseconds and up to 1 second. Happy Eyeballs, for example, uses a biasing of only 50 milliseconds. So you can see that these normal timeout periods for UDP are generous, perhaps to a fault, but they're certainly very generous. So what happens when you get a timeout? What happens when you send a query, you get no answer? Should you ask the same server again? Didn't ask the first time, but maybe the second time, because optimism is infective. Or maybe I should just change the address or the protocol. If I asked in v4, maybe try in v6. Or if I've got multiple addresses for that named name server, I should flip to a different address for the same server. Or maybe the timeout says something else and I should ask a different server. Up to you. There are no rules. And of course, when do you give up? Well, the number of timeouts is typically limited. And normally in resolve.conf, it says 2. But you can configure it up to 5, says the man page. When does people normally give up? Somewhere between 2 and 4 is typical. So it depends on the actual library that you're using and the way you've configured it, but it will try a few times, but not forever. What about resilience in TCP? Well, TCP, once you've done the handshake, you've got a connection and you're sending each other packets. So if you can establish a session, then normally you can reasonably expect a response or an error code. There are times, of course, when TCP will hang and all bets are off, but that's less than reasonable. Now, if you get back an error code, like serve fail, what do you do again? Asking the same server and you've got a TCP connection is kind of pointless, because that server gave you that answer. It's kind of optimistic in the extreme to expect that if you ask again, you might get the same answer. What if I set up a new TCP session to the same address? Would that give me a different answer? That's a different question, because sometimes what you get is different recursives hiding behind the same name or even the same, protocol address and the same protocol. And that happens a lot these days with compound resolver farms. And so oddly enough, you can actually set up a second TCP session and you may or may not see the same server, and you may or may not get the same answer. What should a poor stub resolver do? I don't know. Typically, though, if you get back an answer like serve fail or maybe refused, you might try again even with TCP. You might like to try again with a different authoritative name, but you might try again. On the other hand, you really are thrashing at this point, and maybe the optimism's unwarranted. Bad is bad. Move on with your life. There are other things to do. There are other transports these days, and I've said the magic words here, dot, do, and the unpronounceable DOQ. All I need to say here at this point is that we have a very limited amount of time left, and the universe is only a finite amount of time left before it all decays. That is probably not enough time to discuss these transports in detail, so I won't. So the answer is yes. If more is better when it's too much, well, none of us really know, but replication certainly has its limits. What you typically do as a client is not ask all at once. You serialize to avoid flooding, and clients typically limit the number of queries. Adding more resolvers to resolve.conf, adding more name servers, adding more addresses, adding more protocols typically adds time and delay, but doesn't necessarily improve resilience. Because if you really want resilience, it's not necessarily adding more entries into the replication lists. That just makes life slow if the answer was no. And so there are other ways we can do this which are way, way better. The first, and the DNS would collapse if it didn't do it, is actually caching. So the DNS queries have a strong component of self-similarity. All of you went to ietf.com to find an answer, but not all of you hammered that server, because often the recursive resolver you used simply cached the answer. Here's the answer I received. If that matches your question, I'm just going to serve it here locally. And without that kind of caching, the DNS as we know it wouldn't. Now, caching is always a bit of a balance between, well, I'd like to serve you the answer that's current. And if I cache it for 5 years, it might be the wrong answer, because 5 years is indeed an eternity. On the other hand, if I do cache it for 5 years, the cache becomes very effective. I'm like, I just don't ask the authoritative anymore. So the resolution infrastructure prefers to cache. It prefers to keep it for longer because it can instantly give you the answer. That's faster. And the cache becomes more effective. I take the pressure off the DNS servers. Name publishers, however, want to give you the answer. And if they want to change that answer, they want that answer to be picked up by the system. So the publisher prefers short, even if the DNS doesn't like it. The DNS itself prefers long because that's what makes it work. So that tension actually sits inside caches and TTLs. But before I move to TTLs, let's just understand who caches. Everyone. Stub resolvers, recursive resolvers, forwarding resolvers, even your browser will cache because caching is faster. But it's not mandatory. So who doesn't cache? Folk who don't cache. It's entirely optional. So what is cached? It doesn't actually cache the entire response. It caches the resource record itself and its associated time to live value. What should not be cached? Well, as we've learned to bitter experience, additional sections are generally not trustable. You should not cache those. So that's a sort of a bigger should not. But there are a number of other corner cases where caching is kind of interesting. With that opt section, commonly referred to as EDNS 0, there is an option for the client to place their subnet, or if the client is deranged, their entire protocol address into the query, and that query is passed all the way through the DNS infrastructure right up to the authoritative server. And so if you're using client subnet, which you shouldn't, the answers cache the client subnet value, and the cache can only be used if the subnet value and the query name both match. You can't reuse a resource record when the client subnet value does not match, but you shouldn't be using it anyway, so what the hell. Should you cache NS records from the parent? Well, you should really cache the ones from the child because the parent ones aren't authoritative. I always love the word bailiwick. It's such a wonderful word. In this case, keep your records in bailiwick, cache from the child, and you are better. What if it fails DNSSEC validation? The local recursive resolver performs for DNSSEC validation. This one failed. Should you cache it? Well, typically you do, but you only serve them if the client says, don't check. Set the checking disabled bit in the query, give me any garbage, you'll send back the garbage in your cache. What if the query has no EDNS extensions and the local recursive resolver knows that it's invalid? Yeah. DNS NSEC records can be cached. They're different records to many others because they span a range rather than an individual name. So oddly enough, the names that don't exist is much, much larger than the set of names that are. If you actually cache those gaps, the cache becomes incredibly effective because it starts to cache the entire zone, not only what's in there, but what's not in there. Now, that range is based on the alphabetically sorted list of names so that you know that all the names between A and D don't exist. So b.example.com and so on, the NSEC record will tell you no. If you're using NSEC3, bad idea. You actually sort the hashes of the names and perform entirely exactly the same function. So NSEC and NSEC3 both work in this set. How long do you keep them? The cache time to live. The TTL, which is actually given by the zone publisher, says to the rest of the infrastructure, you should cache these names for this long in seconds. Now, it's merely a suggestion. You can ignore it, you can use it, but that's what the publisher said. So the recursive resolver, the server, the stub, whatever, may shorten or lengthen that cache time according to their own predilection. Most caching resolvers do have a max TTL setting. So if you say cache this name for, I don't know, 20 eternities, the caching resolver will go, nice try, I'm going to use a day or 2 days or some other value that's more reasonable. You can't use negative numbers, of course, but you can use 0. And if you set a TTL of 0, it says, this is a one-off answer. Enjoy it, but don't reuse it. Keep on asking me. And of course, every single cache is not infinitely sized. So in some ways, if the cache fills, older answers may get thrown out. So cache lifetime might be a lot lower than the TTL, even under high load. Replication is coarse. Replication simply says, if you don't like the answer A gave you, try B. But in some ways, we can do better and use the routing system. And while this was incredibly contentious at the time, back then, don't remember when, Anycast is now part and parcel of why and how the DNS operates. So what we do now is set up exactly the same address at multiple locations within the topology of the internet and actually rely on the routing system to take you to the closest instance of that replicated address. Now, the beauty of this is, as long as you inform the routing system, you can bring new instances up on the same address, or you can take them down, as long as you inform the routing system what you're doing, but the clients don't need to know. So new instances can come up, instances can be removed effectively seamlessly. And the client simply goes to the closest active element that's currently serving it. And so from the client's point of view, serial enumeration, try A, try B, try C, God, this is boring, try D, try E, are we dead yet, try F, try G, doesn't work. I mean, with Anycast, you just go, right, any of these, give me the closest, here's the question, give me an answer. So if we can do this on servers, we can do this on recursive resolvers, of course, and, you know, quad 1, quad 2, quad 3, quad 4, quad 5, quad anything, even up to quad 101, and they're probably still going, often has recursive resolvers that all respond to the same address. So you can do Anycast in a number of places, and it basically just works. The other way where we have parallelism is in a slightly different sense, where these days, the amount of DNS and the density of query often exceeds the capacity of single engines no matter how big the silicon. And so a bit like the web server systems that we use these days, we've done the same in the DNS. And a massive amount, almost 75% of the visible recursive resolvers sit inside a subnet with other recursive resolvers that the authoritative server sees. So what's going on is that a huge amount of resolution machinery is actually sitting inside farms, where you have a common front end that takes the queries, the service address, and these workers out the back, where you distribute the queries that you get to one of these workers, that then goes off and actually does the query, sends the answer back from or through the source address of the front end. I don't even need to go through the front end. I can just fake the source address. And so the resolvers actually each can run their own cache. And so what I've done is sort of split the load invisibly. How do you split the load? There's no RFC, there's no standard, go figure. You can use the conventional 5-tuple hash, source and destination address and port numbers, and of course the protocol ID, TCP or UDP, and simply hash on that. You can simply take the source address and nothing else. If you're really willing to unpack the packet and look deeply inside the packet and pull apart the query name, you can hash on that too. Or indeed, you can do adaptive hashing, where you load up engine 1 as hot as it will take. And once that's loaded up, additional names or additional queries, you then load up on the next and the next. So you constantly try and make the engines run hot, not balanced. Because often, as we've been told, hot caching is more effective than balanced low-level caching. So that resolver query farm distribution is actually an interesting question, because if they're all got independent caches, then QName hashing is really effective, because all the queries for the same name go to the same engine. But what about NSEC? What about range? Well, that doesn't work, because if you try to cache a range and you're doing QName hashing, the query will get sent to a different of these farm engines rather than the one that actually holds the NSEC record. If you've got independent caches, IP source address hashing is more efficient than 5-tuple, because if the querier, the stub resolver, is constantly changing the source port address, you might find you're going to different machines again and again and again, and you're actually using every single engine is actually running in the long run the same cache replicated, which is less efficient. But that might be what you want. And there are certainly mechanisms that share the cache across all these resolver farm entities using some kind of multiply of broadcast or multicast technology to maintain all of them with the same cache. But of course, that's challenging to implement reliably. So all of these mechanisms have strengths and weaknesses. There is no RFC standard about this. Go pick your favorite solution and deploy it. And for that, Joao will help you, because that's his job to talk about that. Thanks. So I'll spin this over to Joao.
Okay, thank you, Jeff. Let me see if I can publish the screen. Publish the screen. Yes. Okay, you can see that now. Yeah, I think you can. If only I could switch on video as well. I'll get the hang of these one day. Okay, so hopefully you all be seeing this. I cannot see the comments because I just went full screen. My section will be shorter. It's just an overview of if you wanted to play with this whole thing that was being talked about up to now, where do you go get your toys? So according to what they do, what role they play, different pieces of software are classified in the DNS as stub resolvers, forwarders, recursive resolvers, authoritative servers, and things that do it all, or at least more than one function. Picking Wes's previous diagram so that you can relate to what he talked in an easy way. Let's start with stub resolvers. These are the things that live in end nodes in laptops and computers, perhaps inside browsers or other applications. Initially, they came into existence as just another part of the BSD Unix API, and the calls that were used, and that is still in use, were get host by address, get host by name, get host end, set host end functions. They appeared in 1983 in 4.2 BSD, which incidentally implemented the DNS that was specified in RC 882 and 883, which is not the current version of DNS. So these API calls predate modern day DNS, which came into existence 2 years later. They are still the mostly frequently used calls when working on Unix, but the other OSs have these and some other layers of abstraction on top. So Windows has its own, Mac OS, iOS have their own. You can also get different implementations. There are more modern implementations. One of the most complete ones is GetDNS, which you can download. It's open source. It has also a stub implementation that goes with it called Stubby, and provides a lot of language bindings, so you can use it from different programming languages. It includes, for instance, things like local DNSSEC validation, which is useful to bring that functionality closer to the application, not having to rely on other pieces of software to do it. As someone already mentioned in the chat, Linux introduced recently the systemd resolve service. People have been beaten. It's still early days for this. It has the advantage that it comes bundled with the system, and so if it starts, you already have a local resolver, which has its advantages and disadvantages. It depends how you use it. But right now, it's slightly immature. Some apps do have their own stub resolvers built in. These typically web browsers that want to speed everything up as much as they can. So they have their own built-in cache, and they run their own DNS queries separately from what the operating system might be doing. Interesting, these days, with the expansion of how DNS is being transported and handled, there might be room for the appearance of more modern APIs or different looking APIs. And one of these, which is kind of only considered right now as a transport, which is like of DNS over HTTP, actually for web people will look a lot like a web REST API with some opaque blog of data. But, well, there's a potential to develop a completely new API over that, or even a new DNS. Moving on, forwarders. These sit typically on home routers or perhaps at your ISP. Forwarders fall in between stub resolvers and recursive resolvers, both in where they sit in the network and what functionality they provide to the network. They have some features that usually are typical of recursive resolvers, such as a big local cache. But they don't usually perform the recursive lookups themselves. Rather, they receive them from the nodes behind them that send them queries, and they forward them to a full service recursive resolver. So that's basically why they are called forwarders. Typical implementations of these, the most famous, the most used worldwide is DNS Mask, a piece of software that's produced by Simon Kelly in the UK. And this software is very, very popular because it got picked up early on by home router manufacturers, and it got dropped in, and a lot of people actually use it without even knowing, right? It has an advantage for that kind of embedded device that has limited resources, because it also includes a DHCP server, and those two functions, DHCP and DNS, are something that every home network needs. But it has been evolving, and for instance, it's been supporting DNSSEC validation locally since 2014. So you might actually have that supported in your home router by now. Other implementations include things like bind. Bind you'll see repeated everywhere because it was the first kind of reference implementation out there, and perform all the functions. So it comes up a lot. Mara DNS is another good implementation. A common setup that you see that you didn't used to see earlier on at ISPs is the use of forwarders. So people at ISPs need to provide DNS services for their customers. It's typically been one of the services that ISPs provide, but they don't want to have the hassle of having to cope with the load that comes with the recursive resolver with a lot of clients. So they configure, for instance, things like bind as pure forwarders and let other OpenDNS resolvers take care of the work for them. Typically, these are the OpenDNS people or the quads, the 8s, 9s, the 101, which is, of course, run out of Taipei 101. Moving on, the next set of functionality are the recursive resolvers. Okay, so these are typically either at ISPs or enterprise networks, which are kind of ISPs for only one company, and the open cloud resolver that you see these days being quite popular all across the world. As there has been some discussion already in the chat, it's not entirely complicated thing these days to run your own recursive resolver in your own computer, and some people argue that that's a good thing to do in terms of privacy, because you don't get the networks don't get to see all of your queries because you can hide them. But still, the most common case is that you send the recursive resolver is run by the ISP, and you send your queries through a forwarder or directly to them. The software used in these deployments is a mix, usually, of open source and proprietary software. Sometimes open source hiding behind a front end that's proprietary. That's not unusual. And since Google started doing their Quad 8 thing years ago, there are more and more of these coming up. And there are also commercial services like OpenDNS that will provide not only DNS resolution for you, but also sort of filter DNS resolution. The recursive resolver is, as a concentration point in the DNS process, is also frequently a control point. Sometimes with good intentions. There might be malware detection that prevents some queries generated by bots to go any further, but not always for good things. So you see these the recursive DNS servers commonly being targeted as the place where censorship occurs or data collection. Some of these feeds that are used to control are proprietary, most of them. At least there is one that's being defined on the IDF, so that's at least you can get a picture of how they are used. Implementations themselves, open source, the typical ones are the ones listed there, by far the most commonly used. In closed source versions, some of those, for instance, CQ64, Infoblox, are front ends for open source implementations. Others are fully developed in-house by the companies that are named there. And the last missing piece is the origin of all the DNS data, the authority servers, the publishers, as we were referring to them earlier. In principle, their function is pretty straightforward. You load what used to be a zone file, can be any sort of database, and then serve based on the data that's in there. Don't do anything there else. Don't be more creative. Just read, write. Read from the disk, write to the network. But of course, people have been using DNS for 35 odd years, and the scenarios where people use the DNS go way beyond a simple scheme of arrows like the one we are presenting here. So enterprises have their own routes, they have their own DNS view of DNS to the inside and the outside, which is different. So the authoritative DNS servers have grown in what they do in the terms of functionality. They do split horizon, basically showing different view of DNS inside your network and outside. They control who sees what and when. They will these days often give you different answers based on which ISP you are coming from, where you are coming from in the world, most normally trying to direct you to the content delivery address that's closer to your source. Sometimes not quite getting it right, but trying at least. And it's a place where there has been an explosion of both features, both at the protocol and the application level. Storage backends that used to be flat zone files, text files, and now can be very diverse, and so use SQL databases, anything you can think of. Traditionally, DNS authoritative servers have always also been open source, and the names there for your reference, but they are also closed source. Some of them you see open in internet. The Microsoft version of the DNS server, authoritative server, you see normally inside enterprises that use Active Directory. Active Directory is based off an IETF RFC and uses the DSS-TC mechanism, but Microsoft managed to really hug it closely and then extend it, and it's slightly incompatible with Active Directory, even though for things like bind have a DSS-TC implementation. If you start using too many features, you won't be fully compatible. Then there are all bits of pieces, stuff that gets thrown into the network because you want to scale, you want to do different things, right? One of these are DNS load balancers. Jeff already talked about that. How do we scale? How do we offer increased resilience? Some of them, to be honest, are loaded into load balancers that were meant to be doing something different, typically HTTP load balancers, and initially had DNS implementations that were more tick in the list of requested things than proper implementations. Of course, with time, everything gets better. There is one that I would like to call your attention for, which is DNS disk produced by the Power DNS guys. I think this is the best example of software for the DNS by the DNS people who understand the DNS intimately, and produced a load balancer that takes full advantage of how the DNS works. And this is one of the cases where they actually analyze, for instance, what makes a cache good, and implemented an algorithm that makes use of that. And some of them just use routing techniques. You can do that with your routers, which is outside of the DNS, but for the DNS's benefit. In the not so good part, there are DNS interceptors. People do things with the DNS because it's a control point, as we said before. And this can range from simple things like captive portals in hotel networks that when you try to access the network will intercept your DNS query and send you off to the registration or login page, to censorship, to other things. This is it for part one of the deep dive. We wanted to tell you a lot more. DNS is one of these protocols that looks simple, but then in real life it gets complicated really quick. And so there has been a lot of misunderstandings. We wanted to have a section on myths and misconceptions, but we couldn't fit it in these 90-minute sessions. So hopefully, if there is a part two, we'll go into that part, into both as an implementer, as a protocol developer elsewhere in the IETF, things that people get wrong, things that people think are one way but turn out to be sometimes simpler, sometimes harder. And that will be left for part two. In the meantime, Warren already published in the chat the link to the survey. We would like to find out what you thought, where we can do better. But there is the link again. And that is all for today's session. We can start the dialogue with everyone.
Please, if you have some, and or put them in the chat, and we will try and answer as many as we can get to. As you can tell, we're running low on time. Sure, there must be some questions.
Warren, it wouldn't be the IETF if it wasn't, but some reason You know, we've stunned them.
Well, the mistake was you didn't ask for complaints.
Yeah, that
Right.
was by design. I've been to an IETF meeting before. I mean, it's possible that you covered everything perfectly in a completely understandable manner. I would be surprised. Yeah, there have also been questions during the chat which have been answered.
There you go, Jeff.
I said EDNS 0 client subnet. And if you actually read the RFC about this, you actually find a preamble from, which I think was suggested by the IESG, that says, this is a really bad idea, but we don't actually understand how to unpublish it. Why is this a bad idea? Part of the issue is that if I saw your DNS queries and no one else's, if I saw your DNS queries, there's nothing about your life I couldn't know, because the DNS is everything. And the way the DNS hides this astonishing privacy leak is that each query, as it moves from stub to recursive to authoritative, loses the identity of the end party that started this in the first place. All the authoritative sees is Google's asking me questions, Cloudflare is asking me questions, Comcast ISP is asking me, resolvers are asking me questions, but they don't know who. Now, if I include the identity of the end user, there's no secrets anymore. That's really bad. And everyone can start assembling profiles. That's incredibly bad. So why are these folk doing it? Why are they butchering your privacy? Well, the answer was actually in response to these Anycast clouded servers, OpenDNS resolvers, that if you've made the cardinal sin to use the DNS as a geolocation steering mechanism, which was the silliest idea known to the DNS part of mankind ever, if you overload the DNS with such geolocation steering, then these massive open resolvers make the resultant service run like molasses. You might be in Australia, like I am, but you might be redirected to a server running in Estonia, because that's where the Open DNS resolver sort of thought that it had configured itself when it gave back a geo answer. And so EDNS 0 client subnet has been useful to actually respond to Anycast services, but the cost of that is incredible privacy leak. I think that was a step, not just a step too far, but a gigantic leap too far, because of that privacy leak problem. Others might be a little more benign to it, but it is, in my view, and a totally personal view, a hideous mistake. Thanks.
I would say it can be lessened if it's configured right. You don't actually need to send a /32 IPv4 address to the resolver, right?
Actually, I believe that the RFC says don't.
Exactly.
It says minimum of 24, I believe, is what it says, but it's been a while.
There have been presentations, Warren, that explicitly talk about how often the don't is ignored.
Well,
which is
there's
bad.
a comment in the chat that says it's limited to a /24. Well, you'd be amused what you see once you start looking at the DNS.
Anyone else?
QNAME minimization.
Yep.
That's a
Can you
fantastic
repeat the
question here,
question?
Dan. Because the question is, speaking of privacy, what are your views on QNAME minimization? And it's certainly the case that the DNS is incredibly chatty, because when it asks and does the discovery of who are the right name servers for this zone, like, you know, www.example.com, it actually sends the full query name all the way down from the root servers. And part of the issue about root servers and the amount of information they see, what they see is actually full query names. Now, in terms of a privacy leak, again, you couldn't get much bigger. And it actually doesn't make the DNS any better. The issue about why the full query name was always included is that you didn't know where the zone cut was. So you actually asked everyone the full question, because if a zone actually had a.b.c.d.example.com, if you sent the full query name to the example.com server, it would just give you back the answer. But the cost of that implicit efficiency was a huge leak in terms of privacy. And to be perfectly frank, it was a step too far in retrospect. So I think QNAME minimization is brilliant, personally.
And just a quick clarification for those who weren't paying attention all the way through the presentation, because lots of people miss this. It's only cache misses that get sent to the root, and then only cache misses that get sent to .com, etc. Lots of people. Okay, Wes is going to clarify my clarification.
Resolvers that don't do caching, so if there's still a cache miss, but that's because they refuse to use one. That's a completely different problem. Let me back up one sec, which is that to be double clear that people got Jeff's point. He's talking about ECS, EDNS 0 / the opt record. I posted a link to IANA in the Meet Echo chat. There is a lot of extensions that make use of it, and so Jeff is not saying EDNS 0 is bad. He is saying that ECS he has issues with. So there's like 15. Actually, there's a lot more than I even realized. There's 17 currently assigned specifications for EDNS 0 / opt subcomponents that we are shoehorning.
There are some subtleties there, Wes, and I suppose now is as good a time as any to sink the slipper into a bit of V6. One of the issues around the EDNS 0 UDP buffer size was actually promulgating the fact that if I can reassemble a 4,000 octet message in DNS, then obviously the path between me and you can equally handle the fragmentation of the UDP packet to send those 4,000 octets. And part of the issue is EDNS 0 isn't path MTU handling, but it gives you the fiction that it can. And what we're finding, particularly in V6, because extension headers and fragmentation combined on the public DNS make a hideous story of packet drop, is that it actually might be worthwhile, particularly with V6, to never send a packet larger than 1280 octets, irrespective of whatever EDNS 0 buffer size you might be able to handle. And so realistically, in some cases, the unbounded optimism of 4096 octets in EDNS 0 buffer size is unfounded, and you'd be better off being way more conservative. 512, yeah, it will work. 1280, yeah, it will work. 1500, yeah, may not. Larger than 1500 and V6, Ben.
So Warren, do you want to pick one of the other questions?
I guess so. So Pete Resnick asks, does Kada or Jeff or anyone else do measurement of how much or how little mechanisms like sending the whole name or having recursive servers help with performance of the global DNS?
We did do QNAME minimization as an experiment late last year and started to measure how much of it was around. And it was actually quite disappointing in some respects that we thought it would be, 70, 80%. And it was a lot less than that. Do you remember the answer, Joel, or do I quickly need to go and find it?
I think it was around 30, not more than that.
Yeah, and so everyone is actually saying we support this, but oddly enough, when we try and do a measurement that aims queries in, and we actually see where QNAME minimization should happen, there's not as much of it as we thought, which is disappointing.
So as a follow-up to that, Victor actually posted a comment further up in the chat that QNAME minimization does, however, run into bugs with poor implementations of empty non-terminals, which is
getting better.
True. That is getting better, so possibly QNAME minimization deployment might also be getting better. Would somebody like to explain what empty non-terminals are?
I did explain what an empty non-terminal was. It was in my slides, Warren.
I wasn't paying attention. I was reading email.
It's a label in the middle of a zone with no data added. Because that's one of the common misconceptions, I think, of DNS is that you can't have that every dot has to be a new label, when you're at, or a new subzone when you're adding stuff. And so I did have a diagram that pointed to a label in a zone that had nothing else but sub stuff underneath it. and that is an empty node terminal. You know, key, I actually started measuring key name minimization at USA ISI's root server, and I need to go back and finish it because I did see the beginning of a ramp, and then I haven't measured it since, and that was like a year ago. So I suspect that it's actually done a lot better lately. It's taken a while to get deployed.
Yeah, and there's a question on synthesize a record at the Apex. Unfortunately, we pushed that one to the part 2 thing. Hopefully that happens, because there's always questions of, is that legal? Does it work even if it's not legal? And there are combinations of those things. Hopefully we get to do that on part 2. Because
I found some answers for QNAME minimization. It's 3%.
Right. Oh, 3.
The folk who do it live in Madagascar, Iran, Nepal, Belarus, Angola. It seems that the larger resolvers are way more conservative about innovation and putting new features in their software. And what we are finding is that resolvers that live way out on the edges, where there are much smaller client being served, actually do more of the leading edge or bleeding edge of software than everyone else. So QNAME minimization, 3%. Gee. Now, of course, this was a year ago, August 2019, and obviously it's got a whole lot better since then. Totally.
Yeah, big difference.
Big difference.
Things in the DNS always get better.
Yes, always.
Up and to the right. That way.
I don't know what your timeline plans are.
I guess we are at the time. For everyone who thinks that it would have been better to have a meeting in Madrid, I am actually in Madrid. It's 37 degrees centigrade outside, bound to go to 39 over Saturday and Sunday when the ITF would begin. So perhaps it's not an entirely bad thing that these got moved to November next year.
I would have enjoyed the mic line. I missed the mic line of people wanting to yell at us. So thanks for everybody attending.
Yep. And for those who live in places without a sane measurement system, that's 102 Fahrenheit.
Thanks, guys. Great job.
So I'd like to thank all of the presenters for this.
Thank you for everyone coming.
As we mentioned at the beginning, it turns out that DNS is a huge topic, and also the amount of confusion around DNS is an even larger topic. So we are planning on having a technology deep dives on DNS part 2 and possibly 3 and 27 and 46. Please do fill in the survey. I will paste the link to the survey once more, unless somebody beats me to it. And thank you very much, everyone. See you in Bangkok or the virtual Bangkok.
How about next week, Warren? We'll see each other next week. Remember, there's an IETF next week. This is not the end of the IETF. This is the beginning of the IETF.
Oh, I was hoping it was done. Yep, that's true. I will see you all at the next few meetings, including at the IETF plenary.
All right. Bye, all.
Thanks a lot. Bye.
Wow.
And now, does anybody know how to terminate a Meet Echo session?
Oh no, I'll just
leave?
exit and let you deal with it.
Gee, thanks.
Your problem, Warren. I'm leaving. Bye.